It's like Instagram for space nerds. Well, good evening. Welcome to Space Oddities. Thank you for joining us on this Tuesday evening. Hope everybody's well. Hope you all had a fantastic week. I know in the UK the weather's been a bit more dodgy this week, hasn't it? In the UK,
most definitely.
Yeah.
It's rain, thunder, and lightning.
Oh God, send some this way for God's sake. Oh. Mind you, we've had a cooler week this week here in Spain. It's gone down to about 31, which is it's a bit cooler. And we were able to get some more sleep, but it's still oppressively hot.
I always like to pull out my calculator when you say the temperature and see 32 plus 9.
Yeah, we have to make allowances for the weird American way of doing things. So
just accept it's hot.
Yeah, it's just hot, basically. Anyway, viewers, hope you're all well. Thanks so much for being here. We do appreciate you spending time with us on Tuesday evening. Just to update you on a couple of things. On our Patreon site, we have now added all of the videos that we did for our Moon Month in April. So there are 48 videos there that we put on the channel for Moon Month, and you can now download them. So to get all of those lovely videos, everything about the moon, all you have to do is to join our Patreon site. And as well as that, you get all the presentations that we show on the Tuesday live streams. And when you join, you get a special present from us. That is 2 10x8 lovely astro photographs taken by Space Oddities astrophotographers. And they're yours for nothing. And all you have to do when you join, go to the chat called For New Members, and it'll tell you how you can get your lovely, beautiful astro prints. So there we are. So why not join Patreon and support the channel? Because it would really help us. And
if you join and support the channel and look at the videos, we guarantee that they will qualify you to get your PhD in astrophysics.
Definitely. And in fact, it might go beyond that. You might end up head of faculty at some university. I mean,
you don't even have to take the exam. Just put letters after your name.
You see what we give you on Space Oddities? We give you everything. So Patreon, it's only going to cost you £5.50 a month plus VAT. And you get, as I said, access to the videos, the presentations, a couple of lovely photographs as a present for joining. And there'll be lots of other stuff going on Patreon as well. And all the instructions about how to download all that, again, is in the chat on Patreon called For New Members. So we hope you will support us, because we do appreciate your support, and it helps us keep going and pay our bills and everything else. Another way you can support us, of course, is by clicking the super chat icon that's run with a $sign on under the chat window, and you can make a donation there. Also, you can buy us a coffee, and we're always open to the idea of more coffee. You can scan the QR code here or click the link that's just appeared in the chat to go to our buy us a coffee page, where you can buy us more caffeine in another contribution towards helping keep Space Oddities going, because we do want to keep going. We want to be around forever. But with your help and support, we will grow the channel and do bigger and better things all the time. And every single penny goes towards keeping everything running. And we do deeply appreciate your support. We couldn't do this without you, because we're nothing without you lot. So there we are. You can also, of course, go to the Space Oddities shop, and you can buy yourself a beautiful Space Oddities t-shirt and or hoodie, which are at very reasonable prices there on the Space Oddities shop. And again, you can scan the QR code, or in the chat, just click the link that should have popped up in the chat. And talking of the chat, I just want to see who's around this evening. Who have we got this evening? Right, let's just have a look. Jerry's there. Hi, Jerry. Alan's here. Stuart. Who else have we got at the moment? Gerard, thank you so much for your donation, sir. Much appreciated. Paul, how are you, sir? Hope you're well. Ian's there, and a few others. So that's really good. If you're new to Space Oddities, well, why don't you introduce yourself in the chat? Just say hi. and we might even say hi back if you're lucky. But you know, we always seem to have lots of people lurking in the background watching, but not sort of saying anything in the chat. We'd love to get to know you. So tell us what your name is, a bit about yourself, where you are. We'd love to know where our viewers are. I can look at the stats on YouTube, but it's nice to hear it from our viewers. And just introduce yourself, because everybody here, all the regular viewers, are a nice, friendly, supportive bunch, and we love them loads. So why not just say hello? So that's the housekeeping out of the way. We have to announce a sad thing, though. Roger's not here tonight because he went for an eye examination, I believe, earlier today, and he's not going to be with us tonight. So I'm afraid there will be no gallery or night sky guide tonight. But we'll hold that over to next week. And don't forget, you photographers who've submitted your images to the gallery this week, for which we thank you. They're already on the Space Oddities website, so you can view your images there. And if anybody wants to go and have a look at your images, your friends, your family, people you hate, who knows, tell them I'm a wonderful astrophotographer. Go look at my gallery on the Space Oddities website. And of course, the address of the Space Oddities website, as ever, is https spaceoddities.space, and you find lots of lovely stuff on the website. We will be adding more stuff to the website in the fullness of time. And just to remind you of the Patreon site as well, the address for Patreon, very, very easy, patreon.com/Space Oddities. And thank you for that. Now, what have we got coming up for you this evening? Well, it's coincidentally happened that we are going to tell you tonight the tale of two observatories. One of them is the Nancy Grace Roman Space Telescope, the latest in NASA's Great Observatories series, which is due to launch next year, all being well. And Michael's going to be telling you all about the observatory and its history and everything else tonight. And I'm going to be telling you about the Square Kilometre Array, the biggest scientific project ever undertaken by humans, under construction at the moment. And I'll be telling you all about that, because that's an amazing project too. So you've got two observatories coming up tonight. Before we do anything, of course, is say hello to Lou. So I hope you're well, Lou.
Doing well, thanks. Doing well.
Good. Well, we're going to come back to Lou in just a little while, because Lou has got a very important discovery to announce that is really hot off the press.
Yes, I found my keys.
You found your keys. There we are. Well done, sir. Well done, sir. Do you remember back in the 80s? It was everybody had those key fobs where you whistled and it would beep, tell you where your keys were. Whatever happened to those? Because they were genuinely useful, especially for people who mislay their keys all the time.
I don't know. That was before my time, Andy. Sorry.
Yeah, in your dreams. Yeah, so there we are. All right, well, in time-honored fashion, we're going to go straight over to the news now. So let's go to the news. Just give me a second to set this up, and we'll have a look at what's been in the news. Not many big news stories this week, but some interesting ones. And as I said, Lou's got a really interesting one that's just been announced. So we'll keep you in suspense about that for a little while longer. So here we are. Here's the news for this week. If you could just maximize that, Daz. So the news for the 22nd of July, as you probably know, because we've told you about it, and you know, if you don't know about it, you should do. We have our third known interstellar visitor in the solar system. It's a comet, and it has the name of 3I Atlas. And I showed you, I think it was last week or the week before, a time lapse of the comet as it was then, which is just basically a dot moving against the stars. But the Hubble Space Telescope has had a look at it, and here's the first image from the Hubble Space Telescope of comet 3I Atlas. And I think you'd agree. What do you think, Pan? Isn't that a lovely image?
Certainly is. Yeah.
It's brilliant, isn't it?
Nice coma.
Yeah. So there's obviously large coma surrounding the comet, and the comet is going to reach perihelion, that is its closest approach to the sun, on the 29th of October this year, and it'll take it just inside the orbit of Mars before it returns or before it turns to leave the solar system again. They did originally think it wasn't going to come any closer than the orbit of Saturn, but recalculations of its orbit have shown it's going to approach the orbit of Mars and then go off the tangent, if you like, and leave the solar system forever. But another interesting thing about this comet has come up this week. You see, it's traveling at 135,000 miles an hour, which for a comet is really, really fast. And what astronomers believe is that this makes it an exceptionally ancient comet, because as it's traveling around the galaxy, it accelerates. The galaxy's gravity has the effect of accelerating this comet. And because it's going so fast, astronomers think it's really, really old and may even predate the Earth itself. So this is exceptional news. And obviously, as it gets closer to us towards the end of October, we will be bringing you more images of it, and there'll be lots more science about it, I'm sure. Now, Avi Loeb, the famed scientist who, whenever anything unusual is in the solar system, he screams aliens. He's already said that this is hostile alien technology that's coming towards us. So you can ignore all that. And him just saying that, I've seen literally dozens of posts on social media from different Facebook groups saying alien technology is coming towards us. Things are getting out of hand these days. It's just ridiculous.
Well,
no, it's
look, if it is alien technology, I mean, they don't have a very good aim. So how advanced can they be? They're going to miss us by millions of miles.
I know. But anyway, we always on Space Odysseys bring you the facts. We wouldn't insult your intelligence otherwise. And the fact is, it's a comet. You can see clearly that that is a comet. So there we are. All right, let's move on. Next story. Now, this I'm really thrilled about, but that's just me, probably. You see, there are these two colliding galaxies that are known as the Infinity Galaxy, and if you look at this image, there are two galaxies. You can see their galactic cores, and both galaxies have got this sort of ring around them, and the whole thing looks like the symbol for infinity, obviously to some people. So they call it the Infinity Galaxy. And they know that both of those cores of those two galaxies have supermassive black holes at their centers. That's pretty much expected. What isn't expected is that there appear to be X-ray emissions coming from a third supermassive black hole between the two galaxies, or in the middle there, between the two galactic cores. And what astronomers are saying is this could be the first direct evidence of the fact that supermassive black holes can form when giant clouds of interstellar molecular hydrogen collapses spontaneously under its own weight because of its immense mass and collapses directly into a black hole. Now, this theory has been really in the news over the last year or so, because the James Webb Space Telescope has been discovering these supermassive black holes just a couple of hundred million years after the Big Bang. Now, if you think that one way in which supermassive black holes could form is it's like a hierarchy. So you may start with two solar mass black holes, anything up to about 100 solar masses each. They merge and form what's known as an intermediate mass black hole, which may then merge with another intermediate mass black hole or another solar mass black hole, getting more and more massive all the time. So building up its mass, building through multiple mergers. The trouble is with the black holes, the supermassive black holes that early in the universe, just a few hundred million years old, just a few hundred million years after the Big Bang, the problem with that is there's not enough time for all those mergers to occur to bring the mass of the object up to millions or potentially billions of suns. So it's long been suspected there must be another mechanism by which you can form a supermassive black hole, which could be the collapse of these giant massive gas clouds spontaneously under their own weight into a black hole. And this looks like it could be the first concrete evidence of that happening that we have in the infinity galaxy, this third black hole between those two galactic cores. So I think this is really exciting, but because it looks as though that idea about the way that these black holes can form with their enormous mass may be correct. So this is a really good discovery. Okay, there's just one more story tonight I've got for you. It's a congratulations story. Congratulations to Professor Jessica Dempsey. She has just been appointed the new Director General of the Square Kilometre Array Observatory, which, as I said earlier, is building the world's biggest radio telescope. She takes over from Professor Philip Diamond, who's held the chair for a number of years. She's taking over next June, and she's been serving as the acting head for a little while, but she's now taking over full time. And because Professor Diamond's been doing it for 14 years. She's currently the director of the Netherlands Institute for Radio Astronomy. She's her CV as a scientist is incredibly impressive. And she will be taking over basically the running of this whole organization. And when I saw this in the news, I thought you viewers might like to know a little more about the Square Kilometre Array. We've talked about it in the past, but not in any detail. So I thought tonight this is what we do. We'd have a look at it, which we will do a bit later. Okay, so that's the news for this week. Hasn't been much in the news this week, but some very interesting stories.
Just quick note. I met Philip Diamond about 24 years ago.
Really?
Yes.
Well, look at a name dropper. Look. Hey, look.
Yeah, I know.
Because
it was with the celebs.
It was a speaker at a conference that I organised.
Oh,
long time ago.
Well, I met Heather Cooper loads of times, if that counts.
That's right. And Nigel Henry.
How many times did you meet her there? I bet you didn't get really drunk with her on her homemade wine.
Not quite, no.
I met Santa when I was very small.
I've heard
count?
the stories, though, haven't they?
Yeah.
Where are we going with this, guys? This is supposed to be the kid-friendly show, I think.
Yeah, I know.
Anyway,
it's him. So he's trying to tell me he's met more astronomical celebrities than I have, and that's patent nonsense. So,
I think let's just leave it for now, and then we'll get pistols at dawn.
Yes.
Michael, you can go off people, you know.
Yeah.
So there we are.
Yeah.
All right. Well, I suppose we better get to him now, because it's his turn next. We're now going to tell you, or Michael's going to tell you about.
I thought it was going to be Lou's turn next.
Oh yes, of course we're going to Lou next. You see, you confused me already. All right. Yeah, as we talked about this, as we got you in suspense, this big news story that only hit the news yesterday. Lou, can you reveal what this story is all about, please?
I can, if you bring it up here. By the way, when you're talking about the interstellar visitor, I was sure you were going to say it's Roger, but I guess
no.
Oh, we're back to aliens.
Say for sure it's not Roger.
We're back to aliens. Oh dear.
All right. Can you put my presentation on the screen there?
Yeah. 1 second. Here we are.
There we go. Okay.
Right.
So I am calling this presentation Betelgeuse.
Like it.
It turns out that the star that we've all been watching, well, okay, there's Corona Borealis, but the second star we've all been watching, that we're expecting to go supernova, perhaps today, perhaps in 10,000 years, we don't know, is in the news again. And only recently, only a few days ago, has this new discovery been made. And you are hearing it here for the first time on Space Oddities. So after this show, you will know something about the universe that none, I repeat, none of your friends will know. So this is a story about the red giant, this red supergiant star, Betelgeuse. Okay. Now, here it is.
So I was going to say, or Betelgeuse.
Orbital. Oh, I'm sorry. I forget my British pronunciations. Forgive me. I'm a little off schedule, as they say. Okay. So here it is in the constellation of Orion. It is a red supergiant star. And of course, Orion's kind of in the sun right now. But as the winter approaches, we'll start to see Orion again. And you will notice that Betelgeuse looks red because it is red. It is a red supergiant. It is an absolutely enormous star with a diameter of about 1,100 times the diameter of our sun, a mass of, actually it's probably more like 17 times the mass of our sun. And it is a very young star. It is only about 10 million years old. And this is the case for massive stars. Massive stars collect quickly, move on to the main sequence quickly, which we'll talk about in a moment, and burn their fuel very quickly. So they don't live very long. And this is a star in the final stages of its life, in only, maybe a few million years, which is just the blink of an eye to a star. Here's a little comparison of Betelgeuse to other stars. There's Antares, a blue-white supergiant, Aldebaran, Rigel, and there's our sun. So you get a sense of how large this star is. Actually, I'm turning this into a treatise on the entire star, not just the discovery, because I get to do this. Okay. This is actually...
Look, what do we say about astronomy? No information is ever useless.
Right, that's right. And no astronomer can talk for less than 10 minutes, even asking what his name is.
Absolutely.
So here's a picture of Betelgeuse. Now, this is a star that is somewhat spatially resolved. That is remarkable. This star is has the size of a like a peppercorn held in a mile in distance. So how do we do this? Well, first of all, what you're seeing is a kind of spotted surface. You see these two large spots. And these are believed to represent convective cells of rising plasma gas in this supergiant star. So in the visible and in the infrared, they are bright because they're bringing up hotter material from within the star to the surface. Nevertheless, these white spots, as well as the rest of the surface of the star, are far cooler than our sun. Okay, so it has a much lower surface temperature. Now, how would you take a picture like this? Okay, most Nikon and Canon cameras can't do this. But the Matisse instrument can. This is the multi-aperture mid-infrared spectroscopic experiment, Matisse. It's a spectral interferometer, part of the Very Large Telescope Array, the VLTI, at ESO's Paranal Observatory in Chile. And this is a machine that separates the light from this star, pushes it back together, brings it back together, looks at the interference pattern that they get, and you're able to get much higher resolution when you do that, in addition to using the Very Large Telescope Interferometer Array, which is a series of telescopes that when you put them in phase, you can combine their images into one image. So effectively, you have this huge, huge telescope, which then would have much better spectral resolution. So it is absolutely miraculous that we can do this, but we can. That is an actual image of Betelgeuse. Okay, this is actually another image of Betelgeuse, just to kind of show how big it really is. You can see the orbits of the inner planets there, as well as Jupiter and Saturn. So it's about the size of the orbit of Jupiter. I mean, this thing is absolutely massive. Okay, so we mentioned that this is a red giant star. And what exactly does that mean? Well, as I tell my my students at Marymount, there's just a bunch of stuff out there. It's just stuff. And if you get enough stuff together, you get to be a star because the collective gravity presses in strongly enough to turn on thermonuclear burning in the core. And when you do that, you get a star that is the beginning of its lifetime along this kind of crooked line on this graph here called the main sequence. And all of these stars fuse hydrogen into helium as their energy source. And that's what they do as long as they're on the main sequence. If you have a very massive star, there's a lot of pressure really pushing that thermonuclear burning in the core, making it go really fast. And so that star is not going to have much of a lifetime. It's going to use up its hydrogen very fast. When it does that, it begins hydrogen burning in the shell around the core, helium burning in the core, and the star shrinks because before helium fusion, there is no fusion process pushing outward, so the core shrinks, heats up, and that heats up the outer shell of the star, making it very large because it expands. And you get what's in the upper right corner here, called a red supergiant. And that is what Betelgeuse is in the final stages of its lifetime. Now, these stars, these red supergiants or red giants, spend actually a small fraction of their lifetime in this state as a red giant star. So we're only talking 10 to 100,000 years or so as a red giant star. So that gives you a sense of how long Betelgeuse has before what? Before it becomes a supernova. Eventually, it will fuse all of its helium into carbon. And if it has enough mass, it will fuse other elements, but eventually it will not be able to fuse again. And with no fusion pushing out, there'll be a huge rebound reaction, a huge explosion called a supernova. At that point, Betelgeuse will either become a black hole if it has enough mass, or a neutron star if it doesn't have quite enough mass. The determination as to whether or not it has enough mass or not is something called the Tolman-Oppenheimer-Volkoff limit, the TOV limit. Less than it's a little unclear, but 2.2 to 2.9 solar masses, it becomes a neutron star. More than that, it will become a black hole. Okay. So Betelgeuse has been brightening and darkening over time. We've seen this in the infrared. We've seen it in the visible. It's very clear that this is a variable star and, in fact, is tracked by the AAVSO, the American Association of Variable Star Observers. And there are a number of cycles of its brightness variability. The one that is most fundamental is about 400 days, roughly a year. And that is believed to be due to internal processes inside the star that are making it grow and shrink periodically. And so as it grows, it has a larger surface area and gets brighter. However, there's another period that has been only speculated about until now. And that is a 6-year period of brightening and darkening. And it really hasn't been clear what was causing that for a while. Let me show you these are graphics and some spectroscopic data, but let me show you some actual images here. Here we see 3 images of Betelgeuse. On the top, these is just visible wideband images. And on the bottom, we see these images in, I think it's silicon. And so you can see that the brightness of the star is changing over time. And again, this year by year change is believed to be due to the internal processes of the star that are actually causing it to slightly expand and contract. So that is the 1 year periodicity. I mentioned before that the reason we can do things that are as amazing as seeing the being able to resolve the surface of this star are due to the Matisse instrument, which engages in this process called speckle interferometry. And speckle interferometry, again, separates the light, brings it back together, looks at the interference pattern, and is able to give you a much higher resolution than simply looking at the light straight on. This is a picture, a little bit of a fisheye picture of the Matisse instrument. And it is capable of resolving features as small as 3 milli arc seconds. That is really, really tiny.
That's a complicated piece of kit. My goodness me.
You don't just put that together on the weekend. Okay, here's a picture. So you have this technique, right? The speckle interferometry. That gives you very high resolution, but there's more. You can increase your resolution further by using the VLTI, the Very Large Telescope Interferometer, and by kind of connecting all these 4 telescopes that are at the European Southern Observatory into effectively one large collecting area. And so you have the benefit of a very large aperture, which increases your spatial resolution even further. So these are 2 amazing pieces of technology that come together to give you these amazing images. And so far, I haven't told you anything about the discovery, but I'm building up the tension here. All right, so here it is. The question is, what has been causing the 6-year variability in brightness? A companion star. This was theorized as one possibility that an orbiting star, a companion, it's very common, right, for stars to form as binary pairs. And in fact, these 2 stars almost certainly formed at the same time, right? But this companion star that they have just seen, this is an image from the Gemini Observatory in Hawaii, is not quite a star yet. It's a protostar. And so it's still gathering its mass, compressing, and getting to a point where it could start thermonuclear burning. So it is not on the main sequence yet. It is a protostar. What is so crazy about this is that while Betelgeuse is at the very end of its lifetime, this new protostar, which I think is being called Beetle Buddy, I think is the name it's given, or the more scientific name is Swahara. In either event, they both formed at the same time, and yet one of them is still in the process of becoming a star. The other one is about ready to kick the bucket. So it's rather remarkable. The orbital period of this newly discovered, and this is just days ago, this newly discovered companion. There have been 2 studies done. One said 2,110 days. One said 2,170 days. You do the math and you find out that both of those figures are very close to the 6 years that is consistent then with the observed brightening period and is observational support for that theory. Now, what is that theory? The idea is that as this star sweeps around rather inside the atmosphere of Betelgeuse, it actually pushes away some of the dust in front of the star. So rather than occulting the star where you'd expect the brightness to drop, it's actually pushing away some of the dust in front of the star to make it brighter. And it's believed now, theorized first, now observationally confirmed that this protostar is responsible for the 6-year period in the brightening and dimming of Betelgeuse. There are those in the scientific community that find this interesting and exciting, but do not feel that it is conclusive yet. So we're going to wait on other observations to confirm. That's just how good science is done. But this is very compelling and quite an exciting new discovery. So I'll hand it back to you, Andy.
Thank you very much. We had a question from Derek earlier. Just let me find it. Let me put it up here. I have a question though.
Yes.
If these two stars formed at the same time, why is one still only a protostar?
Oh, because the lower mass stars take much longer to collect their mass.
Ah, yes, of course. Yeah.
If you've got a lot of mass, it just snowballs, as they say, and into being a star.
Yeah.
Much mass it takes one.
Yeah, I can't find the question, but I think what Derek said was, will Betelgeuse turn into a carbon star before it goes bang?
Well, if it's massive enough, it will already have passed that phase in its evolution. It's everything is driven by mass. If it's massive enough, it will have long since bypassed carbon in its core and be attempting unsuccessfully to fuse iron in its core before it loses its fusion energy and becomes a supernova. So it's all dependent on mass. I see another question here from Ian. Won't the big one absorb the protostar? In perhaps something like 10,000 years, I think is the modeling, because there is interaction between the protostar and Betelgeuse's atmosphere. Energy is being pulled from the orbit of the protostar, and yes, it will ultimately dive into and become a part of Betelgeuse. Now, will Betelgeuse supernova before that or after that? We don't know.
And it's amazing how many news articles you see on Facebook groups and things saying, Betelgeuse is going to go supernova at any moment, and this is what it's going to look like in the sky. And of course, as you said, it could go supernova any time within the next 100,000 years, because these things are incredibly difficult to predict, and we don't know enough about the life cycle of red giants to be sure about exactly when a supernova is going to happen. Having said that, and I'm sure you'll correct me if I'm wrong, Lou, but there are certain visible signs that you would see on a star that is imminently going supernova on its surface. And the idea is that because we don't see those, then, it's not going to happen in our lifetimes, and probably not in our children's lifetime or their children. Because, of course, you've got to have changes in the core happening before once it's cycled through burning its elements. You've got to have activity which eventually makes its way to the surface where it will be visible, and we don't see any of that yet with Betelgeuse. So even though it's 623 light years away, if I recall correctly, so what we're looking at is the star as it was 623 years ago. There's absolutely no sign of the sort of surface activity that you would expect from any star about to go supernova. So it's doubtful that we will ever see Betelgeuse ever going supernova, unfortunately.
Right. I can't tell you how many supernova parties I've planned and had to cancel because of this thing.
Any excuse for this.
Well, the thing is, also with, like you were talking about when you were explaining sort of like what they call shell burning, have we ever actually, we have seen Betelgeuse, Betelgeuse, or whatever you want to call it, brighten and dim for whatever reason. And of course, now they've discovered this protostar, which I think is absolutely fascinating idea. Well, it's not an idea, it's there. But it's, I mean, of course, it's been hidden from us because we didn't have the technology to be able to see this thing. But I find it's absolutely fascinating. But also, I mean, Andy took the question I was going to ask about.
Sorry.
What? No, it doesn't matter.
Yeah.
We got the answer from Lou. But yeah, it's. I mean, I'm just thinking when it does go, Orion's going to look completely different.
Yeah,
definitely.
You know, it's going to be fun. I mean, if it goes to a neutron star, then yeah, we should be able to detect that. But Orion won't be Orion with that little red chip on his shoulder.
And we've known it for so long.
Yeah, exactly. It's going to be completely changed the sky.
you
Our winter sky.
You say we should be able to detect a neutron star that has formed. Now, but if you remember supernova 1987A in the Large Magellanic Cloud, it was assumed that a neutron star had formed because the progenitor star, Sandulik, was a low mass star and didn't have enough mass to form a black hole. But they've been searching for signs of that neutron star since 1987, and there's absolutely still no emissions. But no, that's not strictly true. I remember maybe 3 or 4 years ago.
Yeah, that's what I was just going to say. Yeah.
An infrared trace coming from the center of the supernova remnant. But I don't know what happened about that. But as far as I know, that they've not positively identified any neutron star or indeed black hole at the center of the supernova remnant. Now, I know that Betelgeuse is a lot closer, so you would expect it to be maybe easier to detect a neutron star after a supernova event, perhaps. But you know, I don't know. I don't know whether you'll actually detect it or not.
Yeah, I mean, we're gonna. Well, one thing we will definitely get is definitely a brand new big nebula there.
Yeah,
So,
definitely.
which would be absolutely fascinating to observe.
Yeah, definitely.
So
yeah,
it's
and Ian says the last major supernova was seen in 1054 in our galaxy, obviously which formed the Crab Nebula.
Yeah,
so,
well, of course that's M1.
That was the last major one. Yeah.
Yeah, I mean, but that's one that you can actually go back onto the internet, and they've actually done a time lapse from the early 60s up until today, and you can actually see the thing growing. It's an absolutely fascinating little video, and how it's actually changed over those years. So yeah, very very
and Paul says like this. Paul says it would be exciting if all the scientists say it's definitely not going to go nowhere for thousands of years, because then it's bound to go bang before Christmas. So, very true, Paul. By the way, at this point, can I say a big thank you to your donations this evening? Deep Burrito, thank you so much for your generosity, sir. Much appreciated. And of course Gerard. And who else have we got? I'm not sure. Sorry, my screen is lagging a bit at the moment. I must put some more RAM in this machine. It starts to slow down at this point in the proceeding. So thank you for your generosity, much appreciated. And don't forget, if you want to contribute on a regular basis and get all sorts of lovely benefits, you can join the Space Oddities Patreon page at patreon.com/Space Oddities. And thank you very much. Much appreciated. Okay, well, we're going to move on now to talk about the first of our observatories this evening. And we're going to go over to Michael, who's going to be telling us all about the Nancy Grace Roman Space Telescope.
Yeah, just bear with me a second.
Oh, Alan Ledbury, by the way, says, will a nova disrupt the companion? Well, that would be a pretty big supernova, so you might expect that protostar orbiting Betelgeuse to be obliterated, I would guess.
Yeah, definitely. If nothing else, it'll blow all the gas away anyway. So.
Yeah, that's right. Okay, take it away, Michael.
You got that there now?
Yeah.
Yeah, thank you.
Okay, all right. Okay, yes, tonight I'm going to talk about the Nancy Grace Roman Space Telescope. This is NASA's next generation infrared space telescope, launching not until May 2027, I believe now, which will revolutionize our understanding of the cosmos through unprecedented wide field observations. The telescope was originally called W-FIRST for the Wide Field Infrared Survey when it was first conceived some time ago. But and it was but in 2020, NASA decided to name it after Nancy Grace Roman, NASA's first chief of astronomy. And this is the lady concerned. And a few details about Nancy now. She was born in 1925 and died in 2018, so not too long ago. Nancy Grace Roman was NASA's first chief of astronomy and the first woman to hold an executive position at the agency. She played a pivotal role in shaping NASA's space-based astronomy program during its early years. Roman was instrumental in establishing NASA's astronomy program, advocating for space-based telescopes when the idea was still considered radical.
And it was considered radical in those days, wasn't it? It really was.
Yep. She directed the planning and development of the project that eventually became the Hubble Space Telescope, obtaining funding and earning scientific backing for more than 20 years. So, long career. And there's the lady again. Okay. Roman pushed for the use of charged coupled devices, or CCDs, in Hubble, which revolutionized astronomical imaging. She broke the barriers for women in science and mentored countless young scientists, becoming a symbol of perseverance and leadership. Roman became affectionately known as the mother of the Hubble Space Telescope. Okay, got a bit about the history now. Initially discussed in 2010 on the NASA's decadal survey, sorry, I can't say that, recommended as top priority for next generation space astronomy missions by the National Research Council. NASA depends on the scientific community to pinpoint and prioritize key scientific questions and the necessary observations to address them. Every 10 years, NASA and its collaborators request the National Research Council to forecast research priorities, observations, and conceptual missions for the coming decade and beyond, hence the name Decadal. In 2016, the mission was formally approved in February, and it utilizes a repurposed 2.4 meter mirror from the National Reconnaissance Office. In other words, the mirror was originally going to be to form the optical part of a spy satellite, looking down at the Earth rather than up into the sky. In 2024, the construction milestone was achieved in September, with integration and testing now underway at Goddard Space Flight Center. And this is the mirror in question that was sent from the National Reconnaissance Office. This significantly reduced the development time and costs associated with creating the mirror from new.
I wonder if they just went to NASA and said, "Psst, you want to buy a second-hand mirror?"
Yeah, I think so. We don't need this mirror anymore.
Yeah, exactly.
Yeah.
And go.
I'll just play this. This is a short video showing the similarity between Roman on the left and Hubble on the right. Same diameter mirror, slightly different spectrum that it's going to look at. So that's just a little diagram here of how similar it is to Hubble. So bear with me. Just few things about the mirror. In comparing it with the Hubble with the Roman Space Telescope, Hubble used two 2048 by 4096 pixel sensors for its wide field UV imager, and one 1024 by 1024 pixel sensor for the wide field camera 3 in the near infrared. The Roman Space Telescope, although it's the same size mirror, it's actually 1/4 of the weight and the mass of the mirror, because due to advancements in technology. So, and this is a diagram of the size of the Roman detector. If you look at the size compared with the Hubble detectors, it's absolutely massive. 18 4096 by 4096 pixel sensors.
Blimey.
I'll come on to that in a minute. This is just a blow up of that particular diagram, so you can have a look at that. As I say, the primary mirror, 2.4 meters or 7.9 feet. So very similar to the Hubble, and that's the size of the pixels as well. Okay, key features then. Roman will have a massive field of view. It will be 100 times larger than Hubble's infrared camera, enabling rapid sky surveys. It will have advanced spectroscopy, wide field imaging, and spectroscopy from 0.48 to 2.3 micron wavelengths. Powerful platform. Scientists predict one of the major surveys by the Roman Space Telescope may reveal around 100,000 celestial blasts ranging from exploding stars to feeding black holes. Roman may even find evidence of some of the universe's first stars, which are thought to be completely self-destructed without leaving any remnant behind. Cosmic explosions offer clues to some of the biggest mysteries in the universe. One is the nature of dark energy, the mysterious pressure thought to be accelerating the universe's expansion. Called the High Latitude Time Domain Survey, this observation program will scan the same large region of the sky of the cosmos every 5 days for 2 years. Scientists will stitch these observations together to create movies that will uncover all sorts of cosmic fireworks. And also, like Webb, Kepler, TESS, and other space telescopes, data from Roman and the proposed NASA Habitable Worlds Observatory projected for quite a few years' time will be available to both the scientific community and the public immediately after processing. With Roman surveys expected to deliver a terabyte of data every day to Earth, over 17 times as much as Webb, there is a huge opportunity for the public to help sift through this information.
Oh, I feel some citizen science programs coming on there.
Yep. The area of the detector is with the equivalent the angle of that sky that the detector can image is the equivalent area of 90 full moons. Absolutely massive area. Detecting supernovae, transit instruments, galaxies, and evidence for dark energy. Okay, there's two major scientific instruments on Roman. The first is the wide field instrument. It's got a 300 megapixel visible and near infrared camera for comprehensive sky mapping and deep field observations. Also, a coronagraph instrument for high quality imaging and spectroscopy designed for direct exoplanet detection and characterization. These complementary instruments enable both large-scale surveys and precision observations of individual targets. So this is a photograph of the actual primary science instruments. This is the 300 megapixel visible to near infrared imaging camera and slitless spectrometer. So each of those panels are 4096 pixels square. And this is the detector being fitted to the telescope at NASA's Goddard Space Flight Center. And this is an animation showing the difference in the image size that the Roman telescope can produce, but compared with ground-based image and Hubble Space Telescope image. So this is the Hubble Space Telescope version. And if you look at how far it's zooming out,
wow.
And this is the actual full area of the Roman detector.
Oh, stunning.
Yeah.
Absolutely.
It is amazing.
Amazing.
Okay, this is just a bit more about the high latitude time domain survey. With the high latitude, referring to the high galactic latitudes, the time domain survey, Roman will scan the same large region of the cosmos every 5 days for 2 years. Scientists will stitch these observations together to create movies of its findings.
Wow.
The survey's main component will cover over 18 square degrees, a region of sky as large as 90 full moons, and see supernovae that occurred up to 8 billion years ago. Smaller areas within the survey will pierce even further, potentially back to when the universe was around 1 billion years old.
Ooh.
The survey will be split in between the northern and the southern hemispheres, located in regions of the sky that will be continuously visible to Roman. The bulk of the survey will consist of 30-hour observations over 5 days, which is okay, this is the coronagraph instruments, which is one I find rather fascinating, really. Over the past 2 decades, thousands of confirmed exoplanets have been detected. These have been detected using the following methods. 2 main methods I'm going to go through. The radial velocity method, also known as the Doppler wobble method, is a technique used to detect exoplanets by observing the wobble of a star caused by the gravitational pull of an orbiting planet. The wobble is detected by analysing the star's light spectrum for Doppler shifts, which indicate that the star is moving slightly towards or away from the observer. This is just a diagram of the spectrum of that method to detect a planet. And the other method is the transit method, which is a technique used to detect exoplanets by observing the slight dimming of a star's light as a planet passes in front of it in an event called a transit. And this is a little animation showing the actual that works in reality. But the Roman coronagraph instrument is a multi-layered technology demonstration instruments, which more rightly should be called star glasses. The Roman coronagraph is a system of masks, prisms, detectors, and even self-flexing mirrors built to block out the glare from the distant stars and directly image the planets in orbit around them. The coronagraph instrument is a roughly shape and size of a baby grand piano. The widest part of the instrument measures about 5.5 feet or 1.7 meters across. The coronavirus instruments will suppress the starlight so well that it should be 2 or 3 orders of magnitude more powerful than any other coronagraph ever flown on board a space telescope. The 2 flexible mirrors inside the coronagraph are key components, as light that has travelled tens of thousands of light years from an exoplanet enters the telescope. Thousands of actuators move like pistons, changing the shape of the mirrors in real time. The flexing of these deformable mirrors compensates for tiny flaws and changes to the telescope's optics. These mirrors, in tandem with high-tech masks, another major advance, supports the star's diffraction as well, and the bending of the light rays around the edges of the light-blocking elements inside of the coronagraph. The result, blinding starlight, is sharply dimmed and faintly glowing. Previously hidden planets appear. And it's such a complex system. I'm not going to go through this. I'm not going to go through this diagram, but this is the way that the mirror.
Really?
Imagine putting that together.
Ricochet, isn't it?
Yeah.
God.
Yeah, that's the best diagram I could find, unfortunately. So yeah, but that's that. But here's an animation from the W.M. Keck Observatory in Hawaii which shows 4 super Jupiters orbiting a young star, and this is done by the same sort of system where they block the star's light, and their planets appear.
I've always loved that animation.
Yeah.
I think it's an absolutely genius animation that they managed to get images of these 4 super Jupiters.
Yeah.
I've always loved that. That's amazing.
That's right. And okay, this is just an artist impression of what the Roman coronagraph could see. This is the coronagraph itself.
Oh my God.
Yeah, you can see the size of it.
Oh, goodness me.
You know.
And to think all of that has to be aligned with sort of sub-millimeter tolerance, sub-millimeter tolerance.
It's the optics that fascinate me.
Yeah. It's a bit more complicated than a mobile phone camera.
Just a bit, yes. And this is the actual completed instruments being lifted into place into the carrier at Goddard.
Because when you think that coronagraph on its own is about the size of New Horizons, isn't it?
Well, that's true. Yeah.
Wow.
Okay, where is it going? Roman will be positioned at the Sun-Earth Lagrange point L2, approximately 806,000 kilometers from Earth, in a stable halo orbit around L2. This location provides continuous sky access with minimal thermal interference, enable an uninterrupted observation for the planned 5-year mission. And that's a diagram of the L2 position.
It's getting quite busy out there, isn't it, L2?
Yes, and we already have web and something else.
Yeah, there are a few out there, aren't there?
Is that where Gaia was as well?
Yeah, yes, Gaia.
Yeah.
Yes.
Okay, this is just a little animation, if it will work. Yes. Of where L2 is in relation to the Earth and the Sun. Thought that was quite neat animation. Okay. And mission objectives and science goals. Dark energy mapping, survey billions of galaxies to understand cosmic expansion and dark energy's role. Exoplanet detection, discover thousands of exoplanets using gravitational microlensing, and cosmic structure investigating galaxy formation, black holes, and large-scale universe evolution. Future outlook: Roman will revolutionize wide-field infrared astronomy, combining Hubble class resolution with unprecedented survey capabilities. Launch will be on a SpaceX Falcon Heavy, no earlier than May 2027. This groundbreaking observatory will unlock new sights into dark energy, exoplanets, and the fundamental structure of our universe. Here's the picture of the Falcon Heavy, which for most of you needs no introduction. And Roman represents the next chapter in space-based astronomy, building on the legacy of Hubble and complementing the James Webb Space Telescope. And I think that's the last slide. Yeah.
Right. Thank you so much, Michael. That's really interesting. We've got we've got a whole new generation of telescopes, both space-based and Earth-based, coming online over the next few years.
Yeah.
And the Grace Roman Telescope is one of them. Now, Daz has been brave enough to be wading through the US government's request about NASA's budget. What's the general picture with regard to the Roman telescope, Daz, as regards the money?
Well, it's luckily it survived the cuts. But saying that, it survives being eradicated from the future projects. But the money for it to be operated, and also the studying of data after it's actually been commissioned and it's all up and running, has been cut dramatically. So we're still going to get it. How that's going to affect operations is anyone can guess. But once the data we've got the data. Then also we don't know whether it will actually interfere with the operational of when people put in their proposals to do things with it, and also whether or not the data afterwards will be offered to other communities. So it survived being scrapped, but the aftercare, the money has been reduced. One of the one things I will say, Michael mentioned the Keck observatories on Hawaii. They're being scrapped.
Oh no!
No, really?
Yeah, they're being decommissioned, which is completely stunning, because it was using those that we would determine that there was a supermassive black hole at the center of our universe,
Absolutely.
Sagittarius A. So, but yeah, apparently they're actually being decommissioned, and that along with several other telescopes around the US and that, and they're probably going to be sold on to other agencies if they want to take on the use of them. It's a very sad state of affairs, but yeah, we'll have to have a discussion about it sometime.
I'd like to bring in Lou at this point. Lou, I was only made aware of this today. Are you familiar with the NASA Voyager declaration?
I just read a quick headline about it this morning. Tell me more.
Well, it's essentially lots of scientists getting together with a petition to demand that these awful cuts, which will decimate NASA space science and astronomy across the board, as far as the US goes, doesn't happen. And there are lots of famous names on the list, and viewers, American science could do with your support. So if you would like to sign the petition to stop these insane cuts to science in the US going ahead, then if you just Google NASA Voyager declaration, you'll find it, and just sign the petition, because we all have to do our bit to stop American science being absolutely decimated, and with the possibility it may phase cuts that it may never be able to recover from. So this is serious, and with all sorts of space missions and astronomy projects and observatories all under threat for no reason other than the fact that the current American administration hates science and will do everything they can to destroy science, as they're proving with the EPA and other agencies. We can all do our bit now to help our American friends keep the science going in the US. So again, if you Google NASA Voyager declaration, I'm sure you'll find it easily enough. Do us a favor, sign the petition. Let's try and stop this monstrous attack on science from happening.
Yeah. Thank you very much.
The document I downloaded today was it's over 400 pages long, and when you go through it, there's lots of things, and as you said, there's lots of famous names of missions and things like that we all know and love that have been axed. Veritas and was it Da Vinci?
Yes,
Veritas
Da Vinci.
And Da Vinci.
Yeah.
They've both been scrapped. So we've got nothing going to Venus now. So we won't know about the phosphine discoverers that created those missions in the first place. There's also OSIRIS-REx, and well, anything that's had an extension put to it. Event Horizon,
Parker Solar Probe,
that's Solar Probe. They're all, any extensions are going to be scrapped. So OSIRIS-REx has been pushed on to, to meet its next target because it was extended. Juno's gone as well, and they're going to go all the way to their targets, and then they're just going to sail straight on by because there's going to be no one there to look at the data, to get the deep
it's just
deep
awful.
space. That's another thing, that no one's going to be there to look at the transmissions coming back.
If
so
I
we
could
won't know
offer
what they've seen.
just a small ray of hope.
Yeah,
and you're right. This is all so troubling. The Senate Appropriations Committee has joined the House Appropriations Committee. Of course, it's the House of Representatives that has, as we say, the power of the purse, although they haven't been doing much lately. But the Senate and House Appropriations committees have joined together to oppose the deep cuts to the NASA budget and the modification to the Artemis program. So I don't know what effect this will have. There are still things the president can do to delay that, but I think there's a fair amount of support in Congress to push back against these thoughtless, senseless cuts. So stay tuned.
Well, it's like I said,
anyway, let's move on. Time's getting on. I want to say thank you to Gerard, who's just become our new member of Patreon. So thank you very much, Gerard. Your generosity and support, as ever, is much appreciated. And we hope to see more of you over on Patreon. We do have a chat over on Patreon called Astro Lounge, where you can hang about with us. It's a bit quiet at the moment, but the more people we get over there, the better. So if you've got any questions for us, anything you want to say, there's a chat there over on Patreon to get in touch with us when we're not here on Tuesdays. And we hope to have some fun over there. We hope to see you over there. So for a mere £5.50 plus VAT a month, you can get all that and everything I mentioned earlier. So we hope to see you over on the Patreon. And as I said, it all goes towards keeping this channel running. And we did want a way we could keep in touch with you guys, that we can build some sort of community and be in touch with you more than we are. And if you've got any questions at any time about anything to do with space, you can ask them there, and we will answer them. So let's try and build a community over on Patreon, because I think it will be a lot of fun. And as far as downloads go, I mentioned earlier that you can get all the videos we put there and all of the presentations, and we hope to add more stuff soon. So let's have some fun together. So if you consider paying out that each month to support us and join the community, you'll be more than welcome. Anyway, enough about all that. Let's move on. Going to talk to you now about another observatory, which is in fact the biggest, in terms of size and scale, it's the biggest scientific project that humans have ever attempted. So just give me a second to set that up. And I've been following this for a couple of decades now, so I'm really excited to see the progress of this. So let's have a look. If you can maximize that, Daz, it'd be great. Thank you. So this is the Square Kilometre Array. I'm not going to go through it in a great deal of detail. There is obviously a lot of detail, but let's go fairly swiftly through this. It is a giant leap in radio astronomy. In fact, the biggest leap ever taken in radio astronomy. Just give you an overview. It's called the Square Kilometre Array because it consists of lots and lots and lots and lots of radio antennae. And if you were to join them all into one big dish, that dish would be a square kilometre in size, hence the name. But it's not one dish, it's lots of them, but we'll come to that. It's the world's largest radio telescope. This will make it 100 times more sensitive than any existing radio telescope, or indeed any radio telescope ever built. It's been built in 2 locations, mid-frequency arrays in South Africa's Karoo region and low-frequency arrays in the famous radio astronomy site Murchison in Western Australia. So this is an observatory spanning 2 continents, and the scale of this is absolutely mind-blowing. It's going to revolutionize radio astronomy. It's designed to probe the cosmic dawn, and by cosmic dawn we mean that epoch in the universe where there was the most star formation happening, when the universe went absolutely mad about creating stars and galaxies. It's going to map galaxy formation and evolution, investigate dark energy, and search for extraterrestrial signals across unprecedented distances. This is a mad project, but it is a generational shift. Nothing like this has ever been built before, and it is going to transform radio astronomy and lots of other areas of science too. Very brief history. The idea came about between 1991 and 1993. Astronomers formed an international working group, because this is a truly international project, to develop it. They signed the first memorandum of agreement in 2000, and they set up a collaboration internationally. They set up protocols for collaborating internationally to get as many countries involved as obviously they could to share the cost of it. The design phase began between 2008 and 2012. The design was completed in 2012, and the organization that is running the project is known as the SKA organization. It was formally established, and as you might know, its headquarters is at our dear old Jodrell Bank in the UK, where they built a huge building, excuse me, as the headquarters of the SKA organization, which coordinates everything across the world. And it represents 3 decades so far of scientific collaboration. Now, the structure of this is that it is an intergovernmental organization. This means that each participating country has had to submit a treaty for approval to its own parliament. And that has, to be honest, that's been delayed because quite a few countries have dragged their feet over signing the treaties, but all of the treaties have been signed now. And when that was done, construction could formally go ahead. And there are over a dozen member countries of this enormous project, contributing not just the money, but the scientific expertise. And it's committed to exabyte scale data management and open access principles for the scientific community. Yet again, you know, this feeds into what we've been saying the last couple of weeks about citizen science. This data will be open for anybody to analyze. And what do we mean by exabyte scale data? Well, if you know your computer terminology, you'll know that let's go back to megabytes. 1,000 megabytes is a gigabyte. 1,000 gigabytes is a terabyte, and 1,000 those is 1,000 petabytes is an exabyte. So this is dealing with data on an absolutely massive scale. And we'll talk about the technology a little bit in a moment. Okay, so it's a dual continent observatory, and they had to select 2 areas where there was minimal radio interference. They needed radio quiet environments. South Africa's Karoo region met the bill for that, where the mid-frequency dish array is, and that will be known, that part of the project is not surprisingly known as SKA Mid. The Murchison area in Western Australia already had really strict radio quiet regulations because it's already a center for radio astronomy. So that seemed the ideal place to put the low frequency end, not surprisingly known as SKA low. The construction started last year. So far, I think this is a little out of date now, but when this was written, in total there's a planned 131,000 antennas are going to be built, and they've so far installed just over 1,000 of them. But this is only the first phase of the SKA, because once this is complete, and it will be complete in around 2029, 2030, somewhere like that, when that's complete, they want to move on to SKA phase 2, which means just on the Murchison site in Australia, they want to build 2 million antennas, vastly expanding the scale of this project. But that will be for the 2030s. And they've already done some test images with the 1,000 antennas they've already installed, and they've actually got radio images of 85 known galaxies just to test that the thing is working. So this is good news that they've actually got some functionality going, so they know they're doing okay. Excuse me. Let's move on and have a look at the science objectives, the all-important science objectives. First of all, to look at the development of the first stars and galaxies after the Big Bang, seeing deeper into the universe's infancy than ever before. So with luck, this radio telescope may be able to see back actually further towards the Big Bang than even the James Webb telescope. So we may indeed finally see these first stars in the early history of the universe, which is very exciting. Investigating dark energy, which, you know, we talked about a lot on the channel, whatever this mysterious force, if you want to call it a force, causing the expansion of the universe to accelerate, the SKA will investigate that. They want to test Einstein's general relativity at unprecedented scales and perhaps reveal some new physics along the way that we don't understand at the moment. And another really interesting objective is they want to create the first detailed map of magnetic fields that permeate the universe, which do influence galaxy formation. This is not something we have at the moment. So some incredibly exciting objectives there, but this is another one, the search for extraterrestrial intelligence, because the radio telescope will be able to scan millions of radio frequencies simultaneously, looking for signs of intelligent transmission, and also monitor exoplanets around other stars for signals that couldn't be produced naturally. So a very, very exciting use of this telescope will be to look for potentially artificial signals arriving on Earth from across the universe. Now, what's expected from the SKA? In a single survey area, wherever it's looking at, it's hoping to detect over 600,000 galaxies, create the most detailed maps of the universe's large-scale structure ever made, potentially observe planet formation around distant stars, and enable breakthroughs in understanding not just dark energy, but dark matter as well. So this is all really, really exciting. We talked about, Michael talked about the interferometer on the Roman telescope. Well, this is slightly different. This is the SKA's interferometry. This is the system that will allow telescopes in South Africa and telescopes in Australia to function as one big telescope observing at the same time. It's known technically as VLBI, very long baseline interferometry. If you'd like to know more about that, we can talk about that one week. But because well, I find it really interesting anyway. So even though there are thousands of kilometers between the two sites, they will be able to function as one enormous giant radio telescope, which is why it's going to be 100 times more sensitive than any built. And here we are. Here's the headquarters of the SKAO at Jodrell Bank. I'm really unlucky. I've never actually visited Jodrell Bank. I'm sure lots of you will say you have in the chat. The only time I've ever seen the radio telescope at Jodrell Bank is from a train. So I've never actually visited, and you know, it's always been on my list of places to visit. But anyway, this is the new headquarters of the global headquarters of the SKA, and it's not only there to manage the project, it's also serving as a hub for training and STEM outreach programs. So there's lots of stuff to do with education going on there. Now, here's an interesting fact. At any given moment while the telescope in operation, it will be processing more data than the entire internet. Just let that sink in. At any given moment when the telescope's in operation, it will be processing more data than the entire internet. To process that amount of data in real time, you need some very, very, very special technology. And in fact, when the designers of the SKA were designing it, the computer technology to do this processing of this humongous amount of data coming from the antennas knew that the technology did not exist in the early 1990s for this to happen. But they were so confident that computer technology would improve that by the time the telescope was being built, the computing would catch up and give them the technology they need to process the data. So they were being very optimistic. And sure enough, IBM came along eventually and said, oh, we've got these new supercomputers. We think this is what you need. And that's exactly what they've got. They've got so-called correlated supercomputers located at each telescope site. And they're going to combine the data from thousands of antennas in real time. And these machines will achieve processing speeds of hundreds of petaflops. Now, what on earth is a petaflop? Well, a flop is a floating point instruction. So if you like, think of it as a calculation. And the processing speed is hundreds of petaflops, which, as we said, is a huge amount of data. And basically, these supercomputers will be able to process literally many hundreds of trillions of instructions per second. So these are among the most powerful supercomputers ever built. In fact, I think when they go into service, they will be, if I remember rightly, and I may not remember this correctly, but I think they will be 20% more powerful than any existing supercomputer in the world. And you need that sort of power to process the data from thousands of antennas in real time. Because you see, if you've got antennas, let's say you've got antennas spread over a big area in Australia, the signals from those antennas are going to arrive at the computers at different times. But they've all got the same data. So what they've got to do, they've got to correlate each incoming signal and put them together to align them in time, so that the time spans being measured in trillions and trillions of a second, so that it's acting as one big data stream coming in from antennas that are far apart, and therefore their data is arriving at different times. And this is why you need these correlator supercomputers to do that. It's exactly the same sort of idea as the ones used for the Event Horizon telescope to take the image of the black hole in M87 and the one in our own galaxy, using this very long baseline interferometer from radio telescopes around the world. It's the same idea, but this is on a much, much, much bigger scale. Then, having correlated all the data into one stream of data, then you need to process the data, of course. And there are computing facilities near each site, and these will transform the raw data into science-ready products for the scientists. And these will be among the fastest supercomputers in the world, with exaflop capabilities and hundreds of petabytes of storage. This is The SKA, in fact, has been described as more of a data machine than an observatory, because that's exactly what it is. 99% of the work, receiving the signals, is the easy bit. The hard bit is processing the data in real time and then processing it to get it out to the scientists. And there's going to be a global network of specialized computing facilities that will store, process, and provide access to the SKA data for researchers worldwide. Not just researchers, you guys as well. You'll be able to download this data and play around with it as well. Although you will need some quite specialized knowledge. It's the radio telescopes, it's radio data, but you can certainly download the data and have a play with it. It will all be open to the public. And the combined storage capabilities are approaching an exabyte, which is an absolutely huge amount of data. That's just a diagram on the right of how this immense data network they're building all fits together. I won't bore you with the details, but basically it's a global network to firstly correlate all the data into one stream, if you like, process the data and get it out to the scientists. They had to build a special network because the internet we all know and hate is just not up to the job of handling this amount of data. So they've had to build a global internet basically to handle all of this data. And that's all under construction at the moment. So these computing innovations, they have spin-offs. They are driving innovations in other areas: energy efficient computing architectures, real-time signal processing algorithms, machine learning for automated data analysis, data compression and transport technologies, scalable storage solutions for exabyte scale archives. So this, the science, people say, oh, it's a waste of money, it doesn't benefit people. Yes, it does, because the spin-offs from this into data science, into computing hardware, are going to be immense. So this enormous data machine that's being built is going to benefit all of us eventually, which is great. So let's just look at the past to the future very quickly. The conception, early development, 1991 to 2000, 2000 to 2020, technical design, site selection, and the formal establishment of this overseeing umbrella organization called the SKA organization. The construction phase is going on at the moment, and building the telescopes, deploying computing infrastructure, initial science operations. And then at the end of the decade, late 20s and beyond, complete the first phase and move on to the second phase, which will be much, much bigger. And this is all a result of global collaboration. It's a wonderful example of bringing together thousands of scientists, engineers, and policymakers from over a dozen nations to advance our understanding of the cosmos. The technology spin-offs from this are already happening, believe it or not. So let me give some examples of where the spin-offs are going. In telecommunications, SKA innovations in signal processing and high-speed data transfer are already improving wireless network performance and reliability. So we're all gaining from improvements in wireless network performance because of the SKA. Energy-efficient algorithms developed for the SKA are being adapted for data centers, reducing power consumption in cloud computing. Not just cloud computing, of course, it's AI, isn't it? So the push is on to make AI as energy efficient as it possibly can be, because it uses immense energy resources. I don't know whether you saw this in the news, but Meta, the parent company of Facebook, are planning to build an AI data center that's not much smaller than Manhattan, which is really scary. Not scary because of its size, because I'm sure it will bring a lot of benefits in the world of AI, but just the cooling requirements, the water requirements, the power requirements for a data center the size of Manhattan is going to be immense. So the more energy efficient these places can be, the better, and that's that the SKA is helping with that. In healthcare, image processing techniques created for radio astronomy are enhancing medical imaging, particularly in early cancer detection. So these radio astronomy techniques are already being used to improve cancer detection rates, which is great, obviously. And the educational impact as well. You can see some youngsters on the right there having a look at a display about the SKA. they're already inspiring the next generations of scientists and engineers, STEM outreach programs, international training programs for early career researchers, public engagement initiatives at visitor centers, open educational resources, bringing radio astronomy into classrooms worldwide. This is fantastic, of course. And lastly, the future awaits as construction continues and the first scientific results emerge. The SKA stands poised to transform our understanding of the universe and our place within it, a testament to human curiosity, collaboration, and ingenuity on a truly global scale. So there you have it, ladies and gentlemen. That's a bit about the SKA. But there's something else. Next week, I'll be doing a follow-up to this. There's a part 2 to this, which is going to look at the so-called precursor and pathfinder telescopes for the SKA. What are the precursor and pathfinder telescopes? What's that all about? Find out next week. So I'll be telling you all about that next week.
Are we talking about Pathfinder?
Not that Pathfinder.
Okay. Because wasn't the Pathfinder that's in Australia used as sort of like a test bed to give them some idea?
Yeah, absolutely. Absolutely.
Yeah.
Well,
because I can remember when they turned that on in the first night, it made hundreds and hundreds of discoveries.
Yeah, absolutely. You've basically got the ASCAP Pathfinder, which has been discovering lots of fast radio bursts. You've got Meerkat as well. But anyway, let's talk about all those next week because that's really fascinating.
That's true, Paul.
Yeah.
Yeah, I want to see a sea star in space. I want one out on L2.
Well,
yeah.
I'm waiting until they bring out
a sea star at L2.
Yeah. I'm waiting until they bring out a bigger sea star before I buy one. So
it wouldn't require much of a launch, would it?
Yeah. No, not at all. Not at all. Catapult will do it.
It could be a ride share.
Yeah.
So
there you are. So the SKA is. We can all take pride in this, especially if you're British, because that's where the HQ is, of course, at Jodrell Bank. But also, it's a truly international collaboration of thousands of scientists and engineers all working towards one goal of building this incredible data machine. We could all meet up at Jodrell Bank one day. That would be a great idea. I suppose Manchester would be the nearest airport, wouldn't it? I'd have to fly into.
Yeah.
So yeah, we could do that. That's a great idea, Sandra. We can have a Space Oddities day out at Jodrell Bank or weekend out.
I'm supposed to go over to Manchester, Salford, and give some talks at their colleges. And they keep offering, I've done this before, they keep offering, let's take you to Jodrell Bank, and we never have time. So that'd be great.
That'd be great. Well, when you going, Lou, do you know?
It's possible that I'd be going in the late fall, but I suspect it's more likely spring.
Okay. Well, perhaps we can do it in the spring then.
I'll let you know.
Yeah, that sounds like a plan.
We can call it odd.
Viewers, if you'd like to join us tentatively in the spring or whenever Lou goes, we'll give you plenty of notice. But if you'd like to join us at Jodrell Bank for a Space Oddities weekend, that would be absolutely fantastic. We'd love to see and meet you all, because we know you're all lovely people, but it'd be lovely to meet you and prove it. Yeah, that'd be great. So perhaps we'll consider that. And you can buy us beers all weekend.
Yeah, because obviously
you're up for that.
Obviously, since COVID and lockdown, I've known lots of people I've never met.
Yeah, absolutely. Yeah. Absolutely. But don't forget, a couple of weeks ago in London, I did meet up with Bernard and met him for the first time ever after 20 years of knowing him on the internet. So yeah, it's great. Right. All right, then. So there you have it.
Actually, just before you go any further, going back to the beginning of the show, I'm quite upset that neither of you two, Michael and Andy, actually said you met me.
I have met you, yes.
Have I met you?
Yes, I came to your home.
I met you what's the
Whittington, wasn't it? The Whittington Castle.
Right.
Whittington Castle.
Yeah.
Yeah.
See, the
And-
most
and
important
at the,
person, you forgot me.
And at the SPA meeting.
That's
Yeah.
right. Yeah, yeah. The weekend, wasn't it? That was a good one.
And of course, Daz came over here to spend some time here in Spain with me, and we had a lovely time, didn't we, Daz? It was great.
Yeah, fantastic.
And,
do it again soon. Do it again soon.
Yeah, so we'll do.
Yeah.
So there we are. Okay, so I think that's about it for this evening, folks. Sorry, Roger's not here this evening, so we've had no gallery and no night sky guide, but I don't think he was feeling up to it after going for his eye exam. We will hold them back to next week, obviously. But don't forget, as I said, the images are already in the gallery on the Space Oddities website. So if you have submitted an image this week, apologies for not showing it. We'll show it next week, but it is already on the Space Oddities website. Don't forget Space Oddities website, https://spaceoddities.space. Easy. Don't forget the Patreon. Thank you all for your generosity tonight. It's very, very kind of you.
Another little quick one, Andy.
Go on, then.
Apparently, there's been reports on the internet that the total eclipse of the sun on the 2nd of August is going to be visible everywhere, basically. And
everywhere? Sorry?
Everywhere. I got a few messages saying, "Oh, there's going to be total eclipse of the sun on the 2nd of August. It's not going to be visible from the UK."
How can a total eclipse of the sun be visible everywhere?
Exactly. Yes. Anyway.
I have a dilemma about next year's total eclipse. And
yes, I know. Yes, you said.
I can't quite resolve it because Valencia, which is on the line of totality, is 3 hours south of here down the coast. Fine. Not far away. 3 hours on the train. Easy. But it's only going to be 4 degrees above the horizon.
Right.
Right.
And so the sun will be virtually touching the horizon when totality hits.
Go to Greenland.
Well, no. I've decided I've got another possibility to stay here because from here, the sun is going to be 5 degrees above the horizon with 99.1% totality.
That should make a good photo.
It's not the same.
Same.
Just because the US was
You're hoping against hope.
0.9% difference.
In that case, Andy, it'll be a bit like the annular eclipse that I saw in Shetland in 2003, because that wasn't far off from the horizon.
Yeah. So I don't know what to do because I keep seeing all these Facebook groups setting up ready for next year's total eclipse, and everybody's saying, "Oh yeah, we're going to Spain. We're going to Spain." It's going to be bloody crowded over here. I'll tell you that much. And I'm thinking 99.1%. But what I might do is then wait a year and go to the next total solar eclipse in Spain in 2027. There, Alan's just put it up here.
It's southern Spain, right?
Yeah, it just clips the edge of southern Spain. So it's Cadiz, Gibraltar, that sort of area, right the southern tip of Spain. And totality starts at 10:45 in the morning, which is a lot better, which means it's going to be a lot higher in the sky. So I'm thinking I could stay here for next year's eclipse and get 99.1 total, or wait a year and then go to Cadiz the year after. Don't know. I have to give that some thought. Because obviously with 99.1% totality, it's still going to get dark. We will see.
The difference is night and day, right?
Night and night.
Yeah, night and night.
99.1 and 100%. There's no comparison.
Really?
Oh, yeah. He's only bragging because they've had a couple in the last few years.
Yeah.
Oh, well.
So there we are. Okay. Right. So we'll wrap things up for now. Thank you so much for being here as ever. Don't forget us on Patreon. Don't forget you can buy us a coffee. Do all the usual stuff. Do whatever you like. We don't care. So we will see you back here next week. I will be carrying on just a little bit more about the SKA and its precursor and Pathfinder telescopes. Roger will be back with obviously an extended gallery and we'll have some other stuff for you next week as well. And we hope to have a special guest in the near future. I don't know whether there's any news about our guest, Lou.
No, not yet. Our secret guest, but I will keep trying.
Okay, thank you.
Actually, he's one of the, sadly, he's one of the many talented casualties at Goddard Space Flight Center.
Oh, no, really?
Yeah, but he likes to write. He's an author. So, oops, I said too much. Okay.
Okay.
Yes.
Yeah. Just before we go, Alan agrees with you, Lou, and says 99% is not 100.
Yeah, that's correct.
So, all right then, Alan. Thank you for that. I'll probably go down to Valencia. I've already got my accommodation sorted, so I may as well go down there. So there we are. Okay, well, thank you so much for being here, viewers. We hope you have a fantastic week. Look after yourselves, take care of each other. We'll see you back here on Space Oddities at the same time next week. But in the meantime, don't forget, if you are a Patreon member, we have just put all of the Moon Month videos on the server. The address for which to download them is included in the instructions for new members in Patreon. Don't forget, and talking of special months, we've got Mars Month coming up in September. We're going to be getting that together very soon. And in fact, Daz has already started. So we're going to be delivering you Mars Month in September. Everything you could possibly ever want to know about the planet Mars. That's coming up in September. And we're looking forward to it. And we hope you are too. So from all of us at Space Oddities, thanks for being here. Have a fantastic week. Hope the weather's calm.